Well, hello everyone. This is going to be a unit called River Algebra, where we are going to look at some of the basic relations that govern the steady state conditions of river flow and channel flow, and put those together in such a way that we can try to understand how rivers respond to changes. So this will be things like changes in discharge or changes in slope. So we're thinking about things like climate and tectonics and so forth. But to get to the point where we can understand those things, we first have to do some basic math. And as promised in the title, it is algebra. So that's what we're going to be doing today. This unit actually has two parts. This video part is the first one. And then in class, we're going to be doing a bunch of exercises and study problems that will build on this. So it's real important that you get this stuff before we do it in class. Anyway, onward and upward. Well, as David has already talked about, we have two basic regimes of flow in fluids, and before we can do anything further with rivers, we want to know what regime we're in. So we're going to think about the question of whether the typical flows in river channels are going to be laminar or turbulent. After that, we'll do a basic mass balance and conserve mass for water, and then we'll do a basic force balance for the water, and later we'll do sediment, but that won't be in this unit. Okay. So the laminar versus turbulent question. Well, you guys all know how we decide that. We use the Reynolds number, and I'm going to sketch out and just go through a quick estimate of the Reynolds number here for you so that we can get an idea of whether we think rivers are going to be laminar or turbulent typically. And we're going to use the handy factoid in the orange box here, which is the kinematic viscosity of water. So let's just sketch out the Reynolds number, and we know that the basic definition of a Reynolds number is that it involves a characteristic velocity, a characteristic length scale. In this case, we're going to use the depth of the flow, and then divide that by the kinematic viscosity. So the kinematic viscosity is just a kinematic representation of resistance to flow. The velocity and the depth are pretty well defined. And let's just see if we can rough out some sort of characteristic values for these numbers and see whether we expect river flows to be laminar or turbulent. And of course, you guys already know the answer to this, but let's just have a look. Well, how fast do rivers flow? For a variety of reasons, rivers typically flow at speeds of around a meter per second. And it's actually amazing how consistent this is. So for an order of magnitude purpose, like estimating the Reynolds number, a meter per second is a pretty good guess. Depths of rivers vary quite a bit more, from very shallow streams that are less than a meter deep to mighty rivers like the Amazon that can be 30 or 40 meters deep. But if we used a value of 10 meters and noted that the range is sort of 0.1 all the way to maybe 30 meters, we're going to get a reasonable answer from that. And then, as noted above, the kinematic viscosity, which is something you can easily look up, is in MKS units about 10 to the minus 6. Well, you don't have to do a lot of really hard math to work out that this number is going to be of the order of at least 1 million or more, basically because we're dividing through by this very small viscosity. And even if you don't remember whether the critical Reynolds number for channel flow is 1,000 or 2,000, you know from that we're well above it. So we're going to assume from here on that the flows we're dealing with are turbulent. And that's kind of a no-brainer. Okay, so let's move on. This is just a fancier version of the Reynolds number. You've already seen that, but if you want it written out in not in my lousy handwriting, there it is. All right, now let's move on to mass balance and think about that a little bit. The water flowing in a channel, and we're going to use the term prismatic channel to just mean a channel that has a cross-section that looks kind of like a prism. Has to conserve mass, of course, and basically, as we've talked about already in class with mass conservation, that amounts to thinking about inflows and outflows. So the simplest case we can consider is one where the inflow and the outflow are in balance. The inflow, as we've talked about, could be from groundwater, or the outflow could be to groundwater, or it could be inflow and outflow to other tributaries and distributaries. But we're going to assume that we're in steady state, which means that the flow in that case, over here, has to balance the flow out. Or if we want to put it in a little bit more math mathy kind of way, we can write that the sum of the discharge inputs and the sum of the discharge outputs is the same. But what exactly do we mean by the discharge? Well, in a channel, it makes sense to think about the discharge in terms of three quantities: the width, the depth, so the width is b, the depth is h, and the mean velocity. So we've seen two of these already. The velocity here, the depth we saw in the context of the Reynolds number, and the width b, and you might be wondering why we don't use w for that, which would make kind of some sense, but the reason we don't is that w is often used for a velocity component, and b can be thought of as short for breadth. So b times h times u. If you look at the dimensions of this, we have a length in b, we have a length in h, and we have velocity in u, and if we multiply those three things together, we end up with something with the dimensions of length cubed per time, and that's what we've already talked about for the discharge. So we have a discharge that's made of these three components. BH you can also think of as an area. It's the cross-sectional area of the channel. And then the mean speed of the flow. So that's pretty easy. And that's the quantity that we're going to try to conserve. Now, another quantity that will sometimes be helpful is the quantity that you get by taking that discharge, which is capital Q here, and dividing it by the width, B. And the reason is that in many cases we're interested in what's going on in a single slice of the channel. And for that, it's convenient to have an expression for the velocity normalized by the width. That's especially useful if things don't vary too much across the width of the river. So that quantity is traditionally written as little q, and yes, I know this is a symbol that we've used before, but this is the traditional symbol for this discharge. It's called the unit discharge, and it's just the product of the velocity and the depth. So it's hu, and it has dimensions of length squared per unit time. Okay. So now we have our definitions of discharge in order. And whoops, let's not make random marks on the page, but we'll move on here. Okay, I just put this record in. This is something that I showed you in the last spring's class, but it's just a record of water discharge fluctuations in our own local Mississippi River. This is from the USGS gauge in Orinoco, and it's just to give you a sense, first of all, that the world does in fact use discharge the way I defined it, in units of cubic, in this case cubic feet, or length cubed per unit time. In the rest of the world it would be cubic meters per unit time, or cubic meters per second. But here in the US it's cubic feet. Either way, the discharge record is given in those units, volume per unit time. And this just shows you how much the Mississippi has fluctuated at Anoka, and you can get a sense of the range. It's orders of magnitude. And if you want to see the data for yourself, you can go to the website there and look it up. Okay, so where mass balance gets a little more interesting is where we have multiple river channels interacting. And here is a case of tributary channels. So in this case, you can see that the mean direction of flow is from top to bottom. This is a collection network, the typical kind of network that you see in erosional areas. And the channels are joining together in tributary junctions to collect their discharge into a single place. So one thing you should think about is what the relation is between the discharge in the various river channels that we have here. And hopefully you can convince yourself, looking at the little cross sections that I've indicated with the orange bars, that the discharge at section 0 would be the sum of the discharges at 1, 2, 3, and 4. So Q of 0 would equal Q1 plus, and we'll just do dot, 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 through Q4. So those discharges would add up, all the input discharges, 1 through 4, would add up to the discharge at 0. And that's the case for a tributary network like this. We can also have distributary networks where the flow is dividing out into a series of sub-branches. This would be pretty typical for a delta, and this is the Mossy Delta in Saskatchewan. Here, the situation is analogous, but it's the opposite in the sense that we have water coming in at 0 and then breaking up into these various channels. So you should be able to figure out for yourselves, and I won't go through it here, what the relation is between the discharges 1, 2, 3, 4 and discharge 0. So that's mass conservation for tributary and distributary cases. Okay, so now let's move on to momentum balance, and here we have to introduce an additional factor to our diagram of the water flowing in the channel, and that is the bed slope. So in the upper right here, I've indicated a typical situation for bed slope. We have a long profile, as it's called, of a river. This happens to be the James River in Virginia. And the long profile just indicates that the slope is decreasing as we go down the channel. So you can see the relatively steep slopes toward the upstream end of the river, and you can see them giving way to gentler slopes going downstream. And if you, for example, followed the Mississippi down its length, you would find a similar kind of thing. The slopes are much lower around New Orleans than they are up here in the Twin Cities. So the slope is going to be part of our momentum balance, and we want to be aware of how it changes down river systems. This pattern of decreasing slope as you go downstream is not universal and not fixed by some law of nature, but it is very common. Okay, so with that in mind, we're going to go back to our prismatic channel, our little block of water, and we are going to essentially extract this slice here that I've indicated in white and take it out and try to do a force balance on it. So we're going to do a force balance on, in effect, a unit slice of the river. So let's see how that works out. Before we do the force balance, I wanted to just remind you of the critical quantity that we're after, which is the bed shear stress. And we've talked about shear stress a lot, and so this should all be just review. But going back to the basic definitions of stress, we have normal stresses that are either tensional over here, compressional over here, and then shear stresses. These are between blocks of solid material, but the concept of stress applies just as well to solids as it does to fluids. Here is a shear stress on a horizontal plane. In this upper image here, it's on a vertical plane. Here it's on a horizontal plane. And the concept here is just shearing motion, like the motion when you shear one hand over the other. In the case of the flowing fluid, we're after the same thing, but the shear stress now arises not from just a solid block sliding against another block, but from the flowing fluid sliding over the solid boundary. And the boundary we're interested in is the bed. So the bed is ultimately where the resistance to flow arises, and we are therefore after the shear stress on the bed. That is the shear stress exerted by the flowing fluid on this plane and in this sense for the diagram that I've shown. And we've talked about this a lot. Okay. So let's move on. To determine what the shear stress is, we're just going to do a momentum balance. And if we assume the simplest case, the momentum balance is just between the effect of gravity and the effect of friction. So there are two forces, the friction force, which is the shear stress, and the shear stress on the bed specifically, and the gravity force. But it's not the whole gravity force that we want. We want the component of gravity that is acting in the direction of flow. So it's really important that we recognize that we're going to decompose the force of gravity, which is given by this long arrow here, into two components, one acting parallel to the bed and one acting normal to the bed. It's the component here, parallel to the bed, that actually gives rise to the shear stress. That's the component that the shear stress has to balance, because the shear stress on the bed is acting from the point of view of the fluid in this sense. And so the gravity force balances that. I will leave it to you to think about what balances the other force, but it's normal to the bed as a hint. So we're going to use the slope. The slope is the tangent of this slope angle, but the slope for a river is normally given not as an angle in degrees, but as an actual tangent value, which would be the rise over the run. So the slope, as usually reported in a river, would be this distance relative to this distance, so the tangent. And oftentimes it's given as a percentage, which is a common way to express non-dimensional ratios like that. We'll need the depth, and what we're going to do basically is take this gravity force here, which is density times g, the acceleration of gravity, times the volume of water contained in this little prism that I've outlined here, and I'm not going to draw over it, but the prism that's outlined in the dashes. So that the gravity force is just mass times gravitational acceleration, and in this case we're just writing the mass as a density times a volume. So the volume is h times a, and the mass then is the density times that volume. So that makes things pretty convenient. At this point I'm going to clear everything out just to get back to my diagram, because the a can come over and divide the force, and we have exactly what we're looking for, a shear stress, which is a force per unit area. So if we take this gravity component and this little piece here, rho GH, and we then take the component parallel to the bed, and I'm going to leave it to you to work out the trig to convince yourselves that this angle here is the same as this angle here, and that therefore this component, the one that we're after, is the sine component, not the cosine component. And with all that, if we balance the two forces, we arrive at a very simple relation, which is that the shear stress is just equal to density times the gravitational acceleration times the depth times the slope. And I leave it to you, and I strongly urge you to do this, to work out and convince yourselves that this really is not only the force balance that I described, but that the units are correct. So you should always check that. Okay, so that's a pretty convenient momentum balance. It doesn't have too many moving parts. It's actually just got two pieces. And here it is written out with all the terms defined and so forth in a slightly more formal way. So this is the momentum balance that we're going to be using for the rest of our river algebra work. What I would like you to do and think about is to think about the connection between the shear stress and the slope profile that I showed you before. So looking at the same slope profile from steeper slopes to gentler slopes. Whoops. Let's grab our marker. So the steeper slopes over here, the gentler slopes over here. I haven't explained why this is, but we typically see that in the steeper slopes the flow is shallower. As the slope becomes gentler, the flow depth typically increases. You should think about this question. Given that relationship that we just developed, what does that imply for shear stress change down a river? And the answer may surprise you. Now, there is a caveat to this. Normally you don't get something quite this easy in science for free, and in this case, the price is that we have to make some fairly severe assumptions here. And the main one is that since we assumed steady state, and since we assumed that there was a balance between only two forces, basically the two most basic forces acting on the fluid, it's important to realize that that implies that there can't be any other accelerations or any other forces acting on the fluid. And two common cases where there would be other forces like that are illustrated here, and I'm sure you can think of others. But on the left, I have a picture of the Fly River Delta in Papua New Guinea, and you can see that the the flow coming into the delta is much narrower than the flow leaving the delta through its many mouths. And what that means is that the flow is spreading out, and in most cases, because the total width of the flow is increasing, that means the velocity is decreasing. In other words, the flow is slowing down, and what that means is that the flow is actually decelerating as it goes through this reach. So this whole track, as the flow follows along here, is a decelerating flow. And deceleration is a form of acceleration, so certainly that counts. So this would be a situation where that momentum balance might have to be complicated a little bit. Another situation that might not be so obvious is one where you have flow going around a bend, like I've illustrated here on the right. This is a small creek in, I believe, Colorado. And as the flow goes around the turn, in order to make the turn, it has to have lateral forces acting on it. It has to accelerate. It's basically accelerating by making the turn, and that acceleration is not accounted for in our force balance. So those are two exceptions. But what saves us typically, because exceptions like this are not that uncommon in nature, is that if you average over enough distance, typically these effects will average out, and you can go ahead and use that balance that we just described. Okay, well, if you have followed this happily up till now, you might be thinking about the fact that we haven't mentioned the velocity. So we haven't said anything about the speed of the flow, and your ordinary experience, I think, should suggest that the speed of the flow probably has something to do with how much force it exerts on its bed. It certainly has a lot to do with how much force it can exert on you, right? If you're standing in a river or if you're standing in the wind. So it seems like faster flows should produce greater forces, but there's nothing in our force balance that has anything to do with that. So I would like you to think about it. We're going to develop this in the next couple of slides. What would be involved in relating the shear stress to the flow speed? And it should be clear that it's not just a matter of the flow speed, because for one thing, the units wouldn't work. But also, your common experience in life should suggest that there's something wrong with that idea. So let's move down to this last point and think about what happens when you have moving air and moving water, and think about the forces that it exerts. So here's somebody near some breaking waves, and her umbrella's been blown inside out, and it seems like the wind is blowing pretty hard. And if you have any experience with wind and standing in the wind with your umbrella, you might guess that the wind speed is maybe 30 miles an hour or something like that, 20 odd miles an hour to blow an umbrella out and make you feel that the wind is pushing on you. It's probably blowing at a few tens of miles an hour. Not hurricane force, but certainly not in the single digits of miles per hour either. And if you want to convert this to meters per second, 2 miles an hour is approximately a meter per second. So you take the wind speed in miles per hour and halve it to get the meters per second number. Okay. Now, let's compare that with water. I don't know how many of you have tried wading in a moving river, but I would like to convince you that if you looked at this scene that I've shown in this slide, you would not even dream of getting in the water. For reasons that we'll talk about a little bit later, you can tell by looking at this flow, and in particular, you can tell by looking at the wave pattern on the surface, that and I'm talking about these waves here, you can see their crests. These are called standing waves, and the flow is basically flowing through the standing waves, like this. From the size of these waves, you can deduce that this flow is something in the realm of a meter deep. It might be half a meter, might be a little more than a meter, and that it's moving at a speed probably of a couple meters per second. That's much too fast for you to walk in. You would be knocked over right away. If you did that, it would be quite hazardous, something definitely not to try. So, in fact, there's a rule of thumb that we were taught in the USGS when I worked for them, that if the product of the speed and the depth in MKS units was more than 1, you couldn't wade in it. And that's a pretty good rule of thumb to live by. So the speeds at which you can't stand up in water, in which the water is exerting enough force on you to knock you down, are much, much lower, an order of magnitude lower in water than they are in air. And hopefully that suggests to you that there's another effect than speed, and that is, not too surprisingly, the density. So that's what we're going to look at now. So if we just take that experience and say, okay, common sense tells me that the force that water exerts should have something to do with the speed that it's moving, but it also should have something to do with its density. And I shouldn't say water, any fluid, any moving fluid. We could write a sort of crude equation that would say, actually let me clear that would say that the shear stress, so the force per unit area, and I'm writing it as shear stress on the bed, so we're switching our focus from forces on us to forces on the bed, but they scale the same way, can be written as a function of the velocity, we've already said that, and also of the density of the fluid, which we conventionally write as rho. So you could apply the Buckingham pi theorem that David talked about in class to this and work out what kind of relationship this must be. In fact, the derivation that David did for settling spheres is actually not too different from this. But if you just look at the units of these, you can actually pretty well work out what kind of relationship it has to be. The units of stress are force, so that's mass per time squared times length, so it's force, mass times acceleration, and then normalized by area. So force here per unit area here, and this has mass. We can cancel the length here, and we can cancel that square, time squared, and then a length on the bottom. So these would be the Pascal units that we've been talking about. Well, what dimensions do we have over here? We have mass in our density, and that's divided by volume, so it's mass per length cubed. And we have length divided by time in our velocity over here. So we have density and velocity. If you weren't convinced that the density plays a role before, you could be convinced by this, because velocity by itself doesn't have any units of mass in it. So we clearly need this density. If you stare at this for a minute, you can actually see, if you compare the units on the left and the right, it seems pretty clear, get my pen back here, that, first of all, we only have one unit with mass in it, and that is the density. So the density has to enter this linearly, because otherwise there's no way the units can balance. And we also have, let's see, I'll change color here. On the left we have time, but we have time to the second power, and on the right, in our velocity, we only have time to the first power. So that suggests that the balance might involve the square of the velocity to get the time units to balance. And actually, if you just square this, you'll see that the length works out just right, so that's pretty convenient. And we end up with a relationship that looks like, let me go back to my green, we end up with a relationship that looks like tau naught should be proportional to the density, and this is to the first power, so we'll just put a 1 there and be really compulsive about it, and the velocity squared. And in fact, this is the only way that these two units can combine to give the correct dimensions. And if you work through the pi theorem the way David taught you, you could verify this for yourselves. But in this case, it's easy enough that you can just see it by staring at the units. So that's the kind of relationship that we have. And if we think this is close to the right answer, we might then just go ahead and rewrite this with a coefficient. So we'll just call it coefficient times rho u squared. And you're probably used to seeing this combination because we've used this several times as a scale for the stress. Stresses of various kinds scale with this quantity rho u squared. And the shear stress at the bed is no different from that. So that's our relationship, and if we write it out formally and avoid my my handwriting, we end up with this relationship that I show here. This is called a bulk drag law for a moving fluid. It's the drag law that relates the shear stress at the bed, tau naught, to the speed of the flow, and in this case it's squared, and the density of the fluid. So the density is there reflecting your experience that water moving at a given speed will exert much more force on you than air moving at the same speed will. And the velocity comes in as the square. And one bit of common experience you may have for that is that when you bike, for example, as you increase your speed, the drag on you increases faster than the speed does. In fact, it increases quadratically. So if you double your pedaling speed, you're going to have 4 times as much resistance to deal with. So that's why racing bikers try to streamline themselves and do what they can to reduce this drag coefficient over here. So that's the drag coefficient that we've defined. And at this point, it's just a number. We can tell that it's non-dimensional, but we don't know what its magnitude is. So that's the last thing we're going to cover, is a little bit about what controls the drag coefficient in rivers. This is an example of a river with some beautiful sand dunes in it. These were taken from a balloon by my former postdoc, David Morig. It's the Loup River, a beautiful spring-fed sandy stream in Nebraska. Wonderful place to work. And it's got these sand dunes in it that are, you can't tell from this picture, but those are a meter high or so. You should think about whether these dunes would be likely to increase or decrease the drag coefficient. So would this river with these sand dunes on its bed have a higher or a lower drag coefficient than a river with a flat bed? It's pretty hard, as it turns out, to have a flat bed in sandy streams, but it's not impossible. So if the bed were flat, would it have a lower drag coefficient or a higher drag coefficient than this dune-covered bed? And another case, these are some wind bed forms. These are dunes produced by the wind, and drag coefficients apply to wind just as well as they apply to water. Think about which of these two dune morphologies would have a higher drag coefficient, and of course why. The one on the left is dunes that are longitudinal, so the wind direction is like this, and the dunes are parallel to the wind, so they're like ridges parallel to the wind, basically. They are not like ridges, they are ridges. And the one on the right has some dunes that are across the wind, so they're crossing the wind, and these have fairly steep slopes on the downwind side, which you would know if you've ever seen dunes either in a river or in the air, and maybe if you were very lucky got to go sledding down the steep foreset side of the dune. That's a lot of fun. Anyway, those steep slopes are part of the morphology, so the morphology from the side would look like that. It would be gentle upwind and steeper downwind. Which of these two do you think would have a higher CF value, and why do you think that? We will address these questions in class, but that, I think, is all you need to get started with river algebra. So once you've understood all this, bring that knowledge to class, and we'll apply it in various ways to try to understand how rivers respond to change.